Have you ever seen something that just, well, doesn't make sense? Something that seems to break the rules you thought you knew?
Oh, yeah, like defying gravity,
Yeah,
almost.
exactly. Well, we've got a story like that today, coming straight out of a science lab. It involves a fluid doing something, well, something physicists thought wasn't really possible.
Right, it's pretty fascinating. We're going deep today into this brand new discovery about a liquid that seems to remember its shape.
A shape-recovering liquid. That
Oh.
sounds strange.
It is. After being mixed up, shaken vigorously, it just snaps back into this one particular, really elegant form.
And this isn't just theoretical, right? This is actual lab work.
Absolutely. It's all detailed in a paper just published, actually April 4th, in Nature Physics.
Okay.
The work was done at UMass Amherst, led by a graduate student, Anthony Reck, along with professors Thomas Russell and David Hoagland.
So our mission for this deep dive.
Is to really unpack this, figure out what they actually saw, why it's so surprising from a physics standpoint, and, what it could mean for science going forward.
Okay, let's get into it. And to really get why this is so weird, one of the professors, Russell, used a great analogy: salad dressing.
Ah, yes. The classic oil and water problem.
We all know it, right? Oil, water, maybe some spices thrown in. They just don't want to mix. They prefer their own layers.
Exactly. That's thermodynamics kind of telling them to stay separate, minimize contact. But then you shake it.
Right. You shake the vinaigrette and the spices, little bits. They help the oil and water hang out together for a bit, temporarily.
That's emulsification. The particles, the spices, they stabilize the mixture. But it's usually temporary because thermodynamics, that fundamental principle, generally pushes things towards more randomness, more disorder. Think dropping a glass. It shatters, right?
Yeah.
More pieces, more disorder.
Okay. So shaking adds energy, mixes things up, increases disorder for a moment, but then settle back to later.
That's the usual story.
Yeah.
But this new liquid,
Yeah.
it's doing something else.
So this graduate student, Anthony Rake, he was basically making a sort of scientific salad dressing.
Sort of, yeah. But his spices were a bit different. He was using magnetized nickel particles, tiny ones.
Magnetized. Why? What was he trying to do initially?
His goal wasn't really to, upend physics. He said he wanted to engineer all sorts of interesting materials with useful properties by putting these magnetic particles into fluids. A pretty standard materials science goal, actually.
Makes sense. So he mixes his oil, his water, and these little magnets, shakes it up, and then what? Not the usual cloudy mix.
Not at all. What he
Oh.
saw, and apparently kept seeing, was, in his words, a beautiful, pristine urn shape.
An urn, like a vase.
Exactly, like a classical Greek urn. This elegant, specific shape formed spontaneously out of the mixture after shaking.
And it wasn't a one-off.
That's the really wild part. No matter how hard he shook it, how many times, it kept reforming that exact same urn shape every single time.
Wow, okay, hold on. Normally mixing makes things messier, less organized. This stuff is spontaneously creating order, a complex shape.
Precisely. That's the wait what moment. You can imagine him being pretty stunned.
I bet. What did he do? Just stare at it.
Well, probably for a bit. But then, scientific curiosity kicks in. He apparently started walking around the department, polymer science and engineering, asking professors, have you ever seen anything like this?
And the answer was?
A resounding nope. Nobody had.
So that's when the senior researchers, Professors Russell and Hoagland, got involved.
Yeah.
They specialize in this area, right? Soft matter.
Yes, exactly. And what likely caught their expert eyes was that apparent contradiction. Thermodynamics says, go towards random. This system was saying, nope, let's make an urn consistently.
It suggests some other force is just overriding the usual rules.
That's what they had to figure out. It wasn't just a cool visual. It was a fundamental puzzle.
So how do they tackle it? How do you figure out why it's forming an urn?
It became a bigger effort. They pulled in collaborators from Tufts and Syracuse universities.
Bringing in different expertise.
Yeah, especially folks who could run complex computer simulations to
Yeah.
sort of peek under the hood, see what the individual particles were doing at a microscopic level, something you just can't see directly.
And these simulations, plus more experiments, they pointed to the culprit.
They did. It all came back to those nickel nanoparticles, specifically how strongly magnetic they were. That powerful magnetism seems to be the key ingredient.
Okay, so magnetism. How does strong magnetism mess up the normal mixing, the emulsification? What's it actually doing down there?
Well, Normally, like with the spices in dressing, particles go to the boundary, the interface between oil and water,
Hmm.
and they usually lower the energy there, the interfacial tension. Think of it like a skin between the liquids.
Hmm.
The particles help relax that skin, making it easier to
Or
mix.
they're like little peacekeepers between the oil and water molecules.
Kind of, yeah. But these supermagnetic particles, they do the opposite.
Opposite of.
When the magnetism is strong enough, they actually increase the interfacial tension. They make that skin between the oil and water even tighter, more resistant to mixing in a random way.
So instead of helping them mix, the magnets make them want to separate more, but in a specific way.
Exactly. The magnetic forces between the nanoparticles become dominant. They arrange themselves at the interface in a very particular way to minimize the overall energy, including the magnetic energy. And that specific, stable arrangement forces the oil-water boundary itself into that precise urn shape.
So the tiny magnets are basically lining up and collectively forcing the liquid boundary into this shape because it's the most stable configuration for them.
That's a good way to put it. Professor Hoagland mentioned watching how the nanoparticles assemble at the boundary. You could see how this intense magnetism just changes the whole game, disrupting normal emulsification. The urn shape is the system settling into its preferred low-energy state, given these powerful magnetic interactions.
Like the magnetic rules are just stronger than the usual thermodynamic rules in this specific setup.
That's the crux of it. And that's why the researchers say this appears to challenge long-standing ideas rooted in the laws of thermodynamics.
Wow. It suggests those laws might have, well, exceptions or conditions we didn't fully appreciate.
Or at least that other forces, like strong magnetism here, can create states that look like they defy the simple tendency towards disorder. It forces a more nuanced view.
Professor Russell had that great quote, "When you see something that shouldn't be possible, you have to investigate." Seems like they really did.
Absolutely. And it's opened up a whole new line of thinking in their field.
So what are the implications? Is there a practical use for urn-shaped salad dressing?
Huh. Probably not immediately. There aren't obvious immediate applications jumping out, but that's often not the point of fundamental research like this.
Right. It's about understanding the basics better.
Exactly. This is significant for soft matter physics. It shows there are still really fundamental behaviors of materials we haven't seen or understood. It opens, as they say, new frontiers. They've found a never-before-seen state of matter.
So no immediate gadget, but it pushes the boundaries of knowledge itself.
Precisely. And understanding these weird behaviors, these outliers, often leads to completely unexpected breakthroughs down the line. Things we can't even conceive of now might build on this understanding.
It really highlights the value of just exploring, seeing what happens. And this work wasn't done in a vacuum, funding-wise.
No, it had support. They mentioned funding from the U.S. National Science Foundation and the Department of Energy, which, shows the importance of public funding for this kind of basic curiosity-driven science.
Okay, so wrapping this up, the big takeaway for everyone listening. Even simple systems like oil and water with some magnetic bits can hold profound surprises.
Yeah, nature still has tricks up its sleeve. This experiment, seemingly straightforward, revealed this incredibly complex behavior that makes us rethink some core scientific ideas.
And it really came from just noticing something odd, right? That initial surprise.
Totally. A graduate student's unexpected observation, pursued rigorously, led to this potential shift in understanding. It's a great example of how science often progresses, not always planned, sometimes just following the surprising results.
It definitely leaves you thinking, what else is out there? What other basic rules might have twists or exceptions we just haven't stumbled upon yet?
That's the exciting part, isn't it? It keeps science moving forward. There's always more to discover.
And for our listeners, particularly those preparing for UPSC exams, think about this. This is a perfect example of fundamental research challenging established paradigms.
It shows how scientific understanding evolves, the importance of observation, and how asking why about something unexpected can lead to significant shifts. That critical thinking, that understanding of the scientific process is really valuable.
Absolutely. It's not just about memorizing facts, but understanding how knowledge is built and sometimes rebuilt.
Couldn't agree more.
Well, if this dive into shape-shifting liquids got you thinking, please do hit like, subscribe, and definitely drop any questions you have in the comments. We love hearing from you.
Yeah, let us know what you think.
And just a note, all the details we discussed today came from the research highlighted over on earth.com. Thanks for tuning into this deep dive.